Good morning, students. Once again, I welcome you to my video lectures on network analysis basic concepts. And in the last session, we had a phasor and phase concept, phase relationship. So after understanding the phase relationship, next, what is known as phasor notation. So phasor concept is very important for an engineering student studying electrical engineering. So in electrical engineering, very frequently we come across sketching of sinusoidal alternating voltages and alternating currents. And it is a very, as you all know, sketching a sine wave like this, showing amplitude, period, phase relationship. It is a very tedious and time consuming job to sketch sine waves again and again. So is there any easy method of representing sine waves instead of sketching graphically like this? Yes, there is a concept called phasor concept. Phasor, it is a shorthand notation for representing phasors. Technicians and engineers, they use what are known as phasors. So phasors, they used to phasors. So phasors are used to represent sinusoidal voltages and currents of same frequency. One point, keep it in mind, of same frequency, not different, unlike frequencies. For the same frequency, we can use what is known as phasor concept. So this phasor concept was first introduced by Steinmetz. His name is Steinmetz. In the year 1893. He introduced what is known as this phasor notation. What exactly is a phasor? Suppose this is a sine wave. So I have to represent this sine wave by phasor. So you can represent this sine wave by phasor. You represent this sine wave by phasor notation. So in phasor notation, it is very advantageous to add sine waves or to subtract one sine wave from the other. It is very tedious job. If graphically sine waves are represented, graphical addition as well as graphical subtraction, very tedious job. So that is why people go for the phasor concept. Now today I will explain what is this phasor notation. So I can use a phasor to represent this sine wave. It was Steinmetz who showed that a sine wave can be represented by a rotating line segment. So what is a phasor? A phasor is a rotating line segment. Then comes a question, if it is a rotating line segment, what is the length of the line segment and at what angular velocity it is rotating? Suppose you have to represent a sine wave Vp sin omega t. If you want to represent this sine wave having amplitude Vp and angular velocity omega, you can use phasor. And the phasor is a rotating line segment of magnitude Vp. So you have to take line segment length to be equal to the amplitude of the sine wave. And the angular velocity with which the line segment is to be rotated is same as this omega. So omega is angular velocity. It is expressed in radians per second. So what is phasor? Phasor is a rotating line segment. Now I will show the rotating line segment for this sine wave. So this is a sine wave to be represented by phasor. Now this is amplitude. Now I will take a line segment of length Vp. I will take a line segment Vp. First you imagine that this line segment is positioned horizontally. Why it is positioned horizontally, I will explain. Now this is the rotating, this is a line segment of length Vp. So Vp is amplitude, and this line segment is rotated in anti-clockwise direction. It is rotated in anti-clockwise direction. Now it is rotated in anti-clockwise direction with an angular velocity omega. What do you mean by angular velocity omega? Omega, it covers an angle of omega radians per second. Per every omega is expressed in radians per second. So omega, it is rotated like this. Now, if you imagine that this line segment is rotated in anti-clockwise direction, what is the figure that is generated? The figure that is generated by the tip of this rotating line segment is a circle. Now I will sketch that circle. This is the circle. This is the circle that is generated by the rotating line segment. The rotating line segment is like this. Now first, to begin with, at t equal to 0, so arbitrary time, starting time, t equal to 0, it is positioned like this and it is rotated. For example, at t equal to 0, it is positioned like this. What is the angle swept by this rotating line segment at the end of t seconds? At the end of t seconds, it is omega t. It is omega t. Angular velocity is omega radians per second. So, what in t seconds, it is going to sweep an angle omega t. Now, it was Steinmetz who showed that this rotating line segment is going to represent the sinusoidal variation. As you know that sine wave starts with 0, it increases in the positive direction. Next, it starts decreasing in the positive direction, passes through 0. Then in the negative direction, it increases. Next, in the negative direction, it decreases. Is it not? This is what sinusoidal variation. Now, how this rotating line segment is going to represent these instantaneous values. These are called as instantaneous values. Now, how this rotating line segment is going to represent these instantaneous values, you must know what is known as horizontal now component and vertical component of the rotating line segment. For example, this is VP line segment subtending an angle omega t. So what is horizontal component? This is what is called as horizontal component. This is what is called as vertical component. So what is horizontal component? So horizontal component, you know, it is Vp cos omega t. Vp cos omega t is horizontal component, and vertical component is Vp sin omega t. Vp sin omega t. Now don't bother about horizontal component, bother about vertical component. Now this vertical component is going to represent these instantaneous values. Now to start with, now the rotating line segment is here. Now what is its vertical projection? Vertical projection is 0 because it is lying flat. It is lying flat. Therefore, there is no vertical projection. Therefore, it is going to represent this instantaneous value. This instantaneous value is 0. This is represented by this rotating line segment. So, positioned like this. Okay, next, it is rotating. For example, at this position, this value, this is vertical projection. This is vertical projection and it is going to represent this instantaneous value. Next, this is as it rotates at one stage, the rotating line segment will be positioned like this. Then this is vertical projection. Horizontal projection is 0. Therefore, this is going to represent this instantaneous value. Next, it starts rotating in this direction. Now, when it is positioned like this, it is going to represent this instantaneous value. This instantaneous value. That is decreasing values. So, in the same fashion, when the rotating line segment is positioned like this, once again the vertical projection is 0. Therefore, it is going to represent this instantaneous value. So, again, as it rotates with an angular velocity omega in this direction, it is going to represent other instantaneous values. When it is positioned like this, it is going to represent the negative peak. It is going to represent negative peak. And by the time this rotating line segment comes back to this position, it is going to represent this instantaneous value. So in this way, taking a line segment of length equal to the amplitude, it is imagined to be rotated in anti-clockwise direction with an angular velocity omega at any instant of time. The vertical projection of the line segment is going to represent the instantaneous value. This is what is called as phasor concept. Though you need not have to, for example, if a sine wave is given like this, you need not have to sketch like this. Instead, you can sketch it like this. You can sketch it like this. You can sketch. So this is length, this is line segment, and this is length. Okay. Now I will continue further with this phasor concept. Now, having represented the sine wave by phasor concept, it is very convenient to add sine waves of like frequencies and also subtraction. In the next class, I will show you the addition and subtraction of sine waves using phasor concept. Thank you.